So that ends in 617, right? This is the one I want. Maybe Zoom's shitting the bed, I don't know. Maybe I should send an email through eStaff. Maybe it's something wrong with Zoom. Hey, Austin, there you are. Okay, so it looks like I accidentally pasted the wrong link into that Canvas announcement this morning. Must have been one that I still had saved on my clipboard from yesterday. So I'm grateful that you guys are finding these. For everybody else, I'm going to take a second to send an email out through eStaff because I'm sure there are some folks who are still sitting in that other meeting or are confused otherwise. But then we'll get started. Okay. That's nice. Yeah. Yeah, I'm always surprised myself when I wake up in time to do these things. So we have a few minutes while the rest of the class figures out, what how to get here, because I accidentally posted that wrong meeting link. So if there are any particular homework problems, my intent for today, really, because we have all the tools, is just to continue solving problems and trying to get you guys more comfortable with the log rules. So if there are any particular problems you guys wanted to look at, or any particular questions you wanted to ask about, that might be a good time. Nothing so far. Okay, I am going to go ahead and switch over to the document camera. Okay. Document camera's freezing. All right, so there it is. Okay. Connected to camera. No, not that one. So I've been using the document camera a lot lately, and it's been working really well. So I think I'd like to continue using the dot cam instead of the bad markers on the board. That definitely wasn't very nice. But it looks like right now the document camera software is giving me a bit of a hard time. So I'm going to close it out and bring it back up. And that's okay, because we're still kind of waiting for people to drift in from the other meeting. Pop open homework 21 so we can talk about problem 10 a little bit. Is this working? Come on, come on, you can do it. USB device, errors, connect. There we go. All right. So I'll switch into that mode. And it looks like number 10 there, I'm really glad you're asking about this, is getting at something we haven't really addressed a whole lot. I think we just spent one day looking at graphs of logarithms, and I think we just looked at two little graphs. So this is a question that has to do with the graph of logarithms. We're going to look at homework 21, problem 10. So we're asked to graph f of x equals the natural log of x and g of x equals the constant function, 1.6. And I think they want us to approximate the solution, right? Yeah, solve the equation. And this is something that we can do not just graphically, but we can also do this algebraically now. So this is kind of similar to those half-life problems where you had to approximate the age of the fossil by solving an equation graphically. So I'll walk you through what they intend for us to do on the calculator. And then we can take a look at how to do this algebraically by hand. First, a quick reminder, the graph of the natural log of x So the natural log of x is the inverse of e to the x. E to the x is a graph we should know pretty well. The blue graph is e to the x. And then remember, the trick to get the graph of the inverse from the graph of the original is to reflect over this line y equals x. And we saw plenty of that back in the 5.2 homework set. So if it's been a little while since you thought about those things, that's okay, it's understandable. But this red graph here is one that we need to start baking into our brain. That's the graph of the natural log, and every other logarithm looks about like that. If you change the base, just like changing the base in an exponential, doesn't really do much to the shape of the graph. I mean, it might be a little bit stretched out, or it might be a little bit compressed. Changing the base of the logarithm doesn't really do a whole lot to the shape of the graph. So the two graphs that they have drawn there, let me open up my virtual TI-83. So the two graphs that they have drawn there look like this. The ln of x has a vertical asymptote, x equals 0, passes through the point 1, 0, and then comes out here like this. And he will go up and up and up forever, but he does it very, very slowly. Much more slow growing than any other function. So this is f. And then the other graph, g of x equals 1.6, it looks something like this. a constant function, so it's just a horizontal line. And they want us to find this x value, which is the solution to the equation f of x equals g of x, right? Because that's the x value where those two graphs intersect. So that's our goal. And I have my virtual TI-83 here, so we can walk through this together. I would come in here and graph y1 equals ln of x. Then I would come down to y2 and graph the constant function 1.6. I don't know what my viewing window is set to right now. It looks like the standard window, and you see these two graphs, right? Maybe it would be worthwhile for us to play with this a little bit. Try and get a clearer picture. All right, so what we're looking for is this point right over here where those guys touch. So I'll extend out to the right just a little bit more. And that should be good enough. Okay, so you see there a picture very much like the one that I drew. And the point, the x value that I'm looking for is the x value associated with this intersection point. I can fiddle around with the trace function, walk that cursor around. It looks like it's going to be somewhere right around here, right? Here, the x value is 1.59, there's 1.61. Sorry, the y value is 1.59 right here. So when x is 4.91, y is 1.59. So this x value is too small because this y value is too small. If I go a little bit, just one tick further to the right, the x value 5.021, y jumps up to 1.61. So just by playing with the trace function, it appears to me to be the case that our solution should be right around x equals 5. But they want something a little bit more precise. Okay, we'll take a look at that next then. If I wanted to be a little bit more precise about this, I could always come in here to my table. Right, so maybe I'm going to go to table set here and choose to start my table at x equals 4.9. So I come in here to table set this to 4.9, and delta table would be maybe 0.01. And that way I can walk my way through really carefully and try to find exactly where this switches over. So 4.95, too small, 4.96, too big, and 4.96 is off by more than the 4.95 y value. So if I was giving this to 2 decimal places, I would say by trace and table in calculator, the solution has to be 4.95-ish. Okay, so that would be, it's got to be a more convenient way to switch from one screen share to another. So this x value right here is about 4.9. There's one other problem that was requested in chat. Before I switch over to that other problem, I want to show you guys how to do this algebraically, because we have the tools now to find the solution exactly. We need to solve ln x equals 1.6. And this is something that we talked about just recently. At the very end of our last class, we talked about how to solve logarithmic equations. So just like to undo an exponential, we take logs on both sides. To undo a log, we exponentiate. This is the thing that sometimes people call eing both sides. So to undo the ln, I need to put it in the exponent of e. So ln x equals 1.6 is actually equivalent to saying e to the ln x equals e to the 1.6. So it's just like square rooting both sides or squaring both sides. You can take logs on both sides or exponentiate on both sides. And the magic of doing this is that the e raised to the ln of x, that just simplifies to x. So this is e raised to the 1.6. That's the exact value of that solution. And if I want to see how good my decimal approximation from the previous work was, the way I can switch it. Let's just share the whole screen. All right. So if I want to see how good my approximation was from the previous step, I can do this and see my exact solution I know is e raised to the 1.6. So I can come down here, e raised to the 1.6. I get 4.95. 4.953. So accurate to the first two decimal places, right? This is good. Okay. So the other problem we wanted to look at oh, I see. Yeah. I thought I switched this over to number 10, but it wasn't. This is number 1. All right. So was homework 21, number 10. Yeah, this is the one you wanted to see, right, Austin? So we want to solve the base 2 log of 9 minus 2x equals 4. So let me get this stuff out of the way. Oh, this thing doesn't listen. So this is the equation that we wanted to solve, right? Cool. The trick, just like the last one, where we went from ln x equals 1.6 to this e to the ln x equals e to the 1.6, is going to be the same trick that we need here. So to undo a logarithm, we need to exponentiate on both sides using whatever the base of that logarithm is. So the base of the ln from the previous problem is e. So I exponentiated base e on both sides. The base of this logarithm is 2. So I'm going to exponentiate base 2 on both sides. So this is our new operation for solving logarithmic equations. We're going to exponentiate which means to put in the exponent of. So that original problem is equivalent to saying 2 to the log base 2, 9 minus 2x equals 2 to the 4. So it's the exact opposite of taking logs on both sides. 2 raised to the base 2 log of anything is just going to be that thing. So my left-hand side simplifies to 9 minus 2x. And on the right-hand side, 2 to the 4 is 16. Right? It's 2 times 2 times 2 times 2, which is 8 times 2 is 16. And from here, it's a linear equation, right? From here, this is no longer difficult. So I could say this is the same as 9 minus 16 equals 2x, adding the 2x over, subtracting the 16 over. 9 minus 16, what's that gap? It's 7, right? So this is negative 7. equals 2x. And so I'd say x is -7/2. Oh. Yeah, so the money step is from here to here to here, right? I see that I've got a log, and if I want to undo that log, I know I need to exponentiate. I always exponentiate using the same base as the base of the logarithm. Here the logarithm was base 2, so I'm exponentiating base 2, which means I'm going to put everything in the exponent of 2. So the left-hand side, instead of just log 2 9 minus 2x, is 2 to the log 2 9 minus 2x. And the right-hand side, instead of 4, becomes 2 to the 4. So I put whatever was originally here in the power of 2. I do that because 2 raised to the log 2 of anything will just be that thing. These guys will undo each other. And so I just get the inside. And this thing is just a number. I can handle it. And then from here to here, I did 2 little algebra steps. I added 2x to both sides, and I subtracted 16 from both sides. 9 minus 16 is -7. And then -7 divided by 2 is -7/2. Questions on this one?
So like, why is 2 raised to the 4th power?
So on both sides, what I did here is I took whatever was here and I put it in the power of 2. I took whatever was here and I put it in the power or exponent of 2. So just like from here to here,
Oh, okay, all right.
whatever was on the left, put it in the power of e. Whatever was on the right, put it in the power of e. I took whatever was here, put it in the power of 2. Whatever was here, put it in the power of 2. So this exponentiate thing is our new tool for solving logarithmic equations. If your equation has a variable trapped inside a logarithm, at some point you will have to exponentiate to solve that equation. Let's look at one or two more. Let's look at something. Well, maybe we'll go back to something a little more gentle, and then we'll jump ahead to something a little scarier. Yeah, this looks, well, this is an exponential equation. Let's stick with logarithmic equations for today. We've looked a lot at exponential equations. Get in here. Okay, we can build up to that. So, yeah, the basic idea to solve so if you have the log base a of your variable or some shit containing your variable equals some other constant b, we exponentiate base a, meaning we put both sides in the power of a. So that would look like a raised to the log a of x equals a to the b. So whatever it is that's on both sides, that goes in the power of your chosen base. And we always choose the base to match the base of the logarithm we're working with. We do that because these guys kind of cancel each other out. And here we just get x equals a to the b. And since a and b are known constants, this solves the equation. So if we look at the next problem here, they say, how long will it take money to triple if it's invested at 8% compounded weekly? This isn't a great written question because they don't let us know how they're measuring time. But if nothing else is said, you can assume in these interest and investment problems that time's being measured in years. So I need to start with my compound interest formula. Then I'm going to set up an equation. And to solve that equation, we're going to have to fiddle around with some logarithms probably. So remember my compound interest formula. It's like this. This is the value of the account t years later. P is the principal, R is the interest rate, N is the number of times you compound per unit of time. So R here is 0.08, that's 8% written as a decimal. And N is 52 weeks in a year, 53 weeks in a year. I think 52. How many weeks are there in a year? Yeah, 52 weeks. So this function a of t, I don't know what p is. They haven't told me how much they're investing, but everything else I do know. And they want to know how long is it going to take for this to triple. Before we get to solving that, let me just simplify this. So 0.08 divided by 52 plus 1, all raised to the, so I'll do this in steps. This is p times 1.001538462 raised to the 52t, which is the same as, so now I'm going to raise this to the 52, and that will give me my nice simple exponential function p times 1.083220474 to the t. So this is the sort of simplification that we did a lot of back in the compound interest section of 5.3. They want to know how long it's going to take for this investment to triple. Well, this is the value of the investment after t years. The original investment was p dollars. So the investment has tripled when a of t is equal to 3p, right? If p was the original investment, then tripling 3 times that is 3p. So this is the equation I need to solve. I take the function a of t in its simplified form because it's easier to work with, and I set it equal to 3p. The p's are going to cancel, right? I divide both sides by p, and those cancel. I want to rescue this t down from the exponent. So to do that, I'm going to have to take a logarithm. All right, this is an exponential equation.
Mr. File Sticker, I can't see, like, on the far right, right above, the investment has tripled when A of t equals 3p. And I can't see, like, why the 52 is gone now.
So I used this rule, right? A to the b, here, I'll write it in the direction we used it. A to the b times c equals a to the b all to the c. So it's the same algebra rule that we needed to find like effective interest rates to simplify these functions. I took this number and raised it to the 52. because crazy big number raised to the 52 times t is the same as crazy big number raised to the 52 all raised to the t. So this number right in here, this is this number raised to the 52. This is 1.00153 8462, all raised to the 52nd power.
Oh, okay, all right, thank you.
Does that feel familiar from when we were doing those effective interest rates problems?
Yeah, I just blanked out for a second.
That's okay. That's all right. Any other questions so far? I'm glad you asked. It's good. It's fun. That's why we do this. Okay, so my next step then would be to take logs on both sides. You could take natural logs or common logs. I wouldn't bother messing around with the base this thing logarithm. That's weird. So let's just take the natural log on both sides. Oop, I need another closed friend here. There we go. So I just stick both sides inside of a natural logarithm. I take logs on both sides. And then this t is going to come down. So that was one of our properties of logarithms, right? That a logarithm of a power is the same as that power times the logarithm. And this is the magic. The log takes this exponential equation and turns it into this linear equation. So then finally, to finish things up, I divide both sides by this natural log. So I get ln 3 over ln 1.083220474. And this is something we can compute in our calculator. About 13.74 years. Now, some common mistakes that I see when people work problems like these is doing stuff like canceling the ln's here. Remember, those ln's are not multiplying. This is not ln times 3, and this is not ln times 1.08, blah, blah, blah. It's the ln of 3 and the ln of 1.08, blah, blah, blah. So it's function notation. So those cannot be canceled because that is not multiplication. Also trying to recombine these using some logarithm rule as a difference, like log of 3 minus that, doesn't work. So be careful using those properties of logs. Make sure you only use those and only use them exactly as they're written. So this is maybe one of the harder exponential equation problems from that homework, because setting up the exponential equation is a bit tricky and the base is very weird. Right? This 1.083220474 number is not a normal base. But it's really the same as the other exponential equations we've looked at. So I would be happy to work whatever you guys would like to work. My intent for today was really just to solve some problems, try to get a little bit more comfy with log properties and log and exponential equations. Are there any other problems from homeworks 2021 that you guys have been looking at that you'd like to work on a little? See, I don't think we really throw you any major doozies in here. It's the same sort of stuff. Something like this might be nice. Let me change the numbers a little bit so you guys still have the experience of solving it. So let's see if we can solve a logarithmic equation like this. How should I get started? My goal, remember from the end of class yesterday, my goal is to get this down to a simple logarithmic equation where I've got the log of some variable stuff equals some constant so that I can exponentiate. So in other words, I want to isolate this term. So I'd start by subtracting 350 from both sides. Um, 35 minus 7 is 28, so it's negative 280. And then I would divide both sides by 10 to get the log alone. So now I just have the log of x equals a constant. Negative 280 divided by 10 is negative 28. What do I do from here? This is the kind of new step, the kind of important step, one that we've mentioned a couple times today. I want to exponentiate. And this time I'm going to do it base 10, because when I see the log without anything written there, I know that that's the base 10 log. And so 10 raised to the base 10 log of x, that's just x. So I get x equals 10 to the negative 28, which is a very small number, right? That's 0.28 zeros and then a 1. Okay. So I feel that we're a little low steam this morning, but I want to do everything I can to try and get you guys comfy on this homework. So please talk to me a little bit. What sort of things are we going too fast? Is this too far forwards? Is this going too slow? Is this too far back? Is there something that feels weird or something that we would like to talk about? What's going on?
Maybe we could like go a little farther ahead.
Okay.
I feel like I just like we have plenty of problems on this. Like it's just a matter of me reviewing them and practicing them on my own. But yeah, I'd like to kind of see some more of the newer stuff.
Okay. Well, in truth, this is the last bit of stuff that we're going to talk about having to do with logs and exponentials. So if we really do feel, and if other folks have an opinion on this, please do chime in, that we've had enough practice with these things, then it's time to start talking about exam 3. So I did want to talk about that today, and I guess these last few minutes, that's what we should do. So exam 3 is going to be next week. And it's going to be on MML, on my math lab. It'll be during our normal class time. And keeping it time controlled is one of the ways that I can help encourage academic integrity. So it is important that you take the test between 10 and 11. It's going to be using HonorLock. So this is a browser extension you can download for Chrome. So you might want to go ahead and download HonorLock. And then I'm going to get you guys HonorLock tokens. So normally you have to pay for HonorLock. You pay something like $15 per test or something. But because this wasn't originally an online course, of course it would be massively unfair for me to ask you guys to pay for it. So the college has secured some HonorLock tokens. This is also how we're going to do the final exam. So it's a good idea to get practice with this system at least once before the final. It will be, let's see, so during class time, right? So from 10 to 11 a.m. And I'll probably open it 1 or 2 minutes early and leave it open 1 or 2 minutes late, just in case there's anything difficult like that. And then the other thing I'm going to ask you guys to do is to scan and upload your Scratch work. I want to see, I need to see work for all problems. Now, normally we would do an in-class activity before the test, and we would also have a little project before the test. Obviously, in-class activities aren't really going to work if we don't have a class to be in, but I will try to think of some way we can do something like a project. Maybe I could upload something to Canvas for you guys. It most likely won't be collected for a grade, but it would be something that you can work on, and I'll give that out probably on Monday, whatever form of that we're going to have. The exam is going to cover just the stuff that we've been talking about. So the one-to-one functions, inverses, exponentials, and logs. So everything that we've done since the previous exam, naturally. Any questions about that? Because after this, the next thing we're going to talk about is totally different. We're going to start talking about systems of equations and systems of inequalities. Okay, so maybe Monday we will talk about the project and try to get ready for the test. Wednesday will be just straight review for the test, so you want to bring questions from all of those homeworks that we've had over the last few weeks. And then Friday during class time will be the test itself. Yeah, what's up? If you don't have a webcam and you don't have access to a webcam, we can figure something out. So HonorLock does have a way to get around that. They don't necessarily require a webcam, but yeah, I appreciate that. If you don't have a webcam, let me know. ASAP. So I appreciate that. And if you could also send me just a Canvas message. That way, when I register you for HonorLock and I get the tokens set up, I'll be able to tell the HonorLock people that you don't have a webcam, and they'll be able to write in the necessary exceptions. So I haven't bumped into this issue myself, but I have heard of other professors who had students that didn't have a webcam but needed to use HonorLock, and there are ways around it. We just got to tell the HonorLock people ahead of time. Okay. Any other questions? Cool. All right, then I will see you guys on Monday. Please make sure you're working hard on those homeworks. I will probably leave all the log and exponential stuff open until next Friday when we have our test, so you can continue to work all through next week. But please make sure you work all of those and work them earnestly. Make sure you're getting something out of doing the work. And as long as you do that, I think everything will be just fine. All right, if you have any tech issues, let me know. Download the HonorLock browser extension for Chrome. Make sure you can install it and that it works okay. And yeah, that is it for today. All right, I will see you guys on Monday.